Hi, I'm Brigid Teaken. I am in the Finite Element Analysis class for the summer of 2026, and I'm modeling a foot prosthetics deformation when a person is just standing on it. I use 2D deformable shell elements to simplify the model. It includes 3 different parts. This is what we will end up with. The different parts I used were a spring connector, the base plate, and the top plate. For the spring connector, you can see that it is just a regular triangle. The base plate is a total length of 25 centimeters and an overall height of 2 centimeters. The top plate has an overall length of 12 centimeters and an overall height of 8.75 centimeters. Overall, all of these parts have a thickness of 7.5 millimeters and an overall height of 10.75 centimeters. The spring connector is to represent the connection between the foot prosthetic and the lower limb prosthetic. It also helps the spring be connected to the top plate as well. Up next is the properties. So I'm using layered carbon fiber, which has a mass density of 1,550 kilograms per meter cubed and a Young's modulus of 4 gigapascals. Next, I created the section, which was the layered carbon fiber, what I just created in the materials, and has an overall thickness of 8 centimeters, which is the overall width of each plate in the prosthetic. Additionally, in the property manager, I created a body mass or inertia for the spring connector, which has 200 newtons isotropically applied, and it is used to create a realistic body weight and in turn result in realistic deformations. Next is the assembly, where I created 3 instances of the spring connector, the top plate, and the base plate. I also created a reference point down below. In the assembly, I translated and rotated the top part to line up with this base plate right here and this line here, where in the prosthetic, the top plate would be screwed into or bolted to the base plate. Additionally, I translated the spring connector to be 2.6 centimeters above the top plate, which is the length of the spring that we are going to be using. I created the reference point, known as ground reference, to assist in unified reaction force measurements at the end and easier creation of boundary conditions. So moving on to steps, I only created one step. I named it loading. Within this step, there is a time period of 3 seconds with an incrementation of 1e to the 7th and an increment size of 0.01 to display the overall animation. Next is interaction. This is probably the busiest section for me in this model. Within the interaction, I created a tie and a coupling constraint, as well as 1 spring and 2 dampeners. The tie constraint connects the top plate to the base plate where they are tangent to each other. Here you can see I picked the bottom part of the top plate and I connected the top part of the base plate right here, this line, and this is to tie them together to prevent them moving apart and to replicate what would happen if they were bolted as in the regular or real life prosthetic. Next, I created a coupling constraint from the ground reference to the flat edges of the base plate. This is used to constrict horizontal, vertical, and rotational degrees of freedom. Because these are shell elements, you don't need to constrict rotation, but the point is selected, so U3 has to be selected as well because the point can technically rotate. Using the coupling allows for the reaction forces and displacement to be referenced with the ground reference and unified for visualization purposes. Within the interaction, I also created a spring, which is called the spring and upper shock. This spring connects the spring connector and the top plate. It is the only spring in the prosthetic. I added a dampener or shock absorber to create a more lifelike scenario where the spring will be compressed when a person is standing on it. The spring stiffness was 35,000 and the dash pot or the dampener coefficient was 4,000. The next dampener I created was the lower shock, and it has a dampener or dash pot coefficient of 950. This dampener helps the plate reach an equilibrium, much like the upper shock when the person is standing on the prosthetic. I did have to mess around with the dampener values for a while, and you can have an overdamped where the dampener dampener is too firm and there will be no oscillations, which means that the part will not exceed its deformations, but will instead just go to exactly what its deformation would be. Additionally, you can have underdamp where there will be multiple oscillations, and I found that the spring connector part would pass through the top plate, which is very unrealistic. So what you're really looking for is a dampener that will allow deformations slightly larger than what would be expected at equilibrium, but will then return to equilibrium without multiple oscillations. It will only be one oscillation. Next is the loads, and I created one load and two boundary conditions. The load I created, I called the weight, and it is negative 700 newtons to represent the overall body weight. And I applied it to the spring connector. By applying it to the spring connector, it represents what the lower limb would apply to the foot prosthetic and create a realistic deformation and applied load. Next are the boundary conditions. The first boundary condition I created was the ground, and I selected the ground reference point where I constricted deformation in the vertical, horizontal, and rotational directions. The second boundary condition I created was to stabilize the spring connector. This prevents the spring connector from moving left or right and forces the part to only move up or down. Because I made the spring connector rigid, it does not matter where I applied the load on the spring connector because it is only allowed to move down. Thus, any weight or load applied will automatically force the overall part to move down. Next, I went to the mesh controls, and I used 3 different types of meshes. For the spring connector, I used CPS 3 elements or linear triangular. These are very stiff elements, but because it is one part and is only moved down, I used a singular element to represent overall deformation. The next element type I used was linear quadratic or CPS 4. These are quadrilateral dominated element types where they have slightly more deformation ability than the CPS 3 elements. The CPS 4 elements better model deformation of the part. The last element type I used was CPS 6 or quadratic triangular elements. These are also very deformable, similar to the top plate. However, the top plate was having trouble with some nodes, so it could only handle the CPS 4 instead of the CPS 6. These elements, just like the spring connector, are triangular. Next is job, where I did submit it and run the animation. And I would go to the results and visualization. Here you can see the undeformed, and here's the deformed with the displacements. You can see how the top part moves to the right while the spring connector moves down, and the spring is somewhat rotated in a way as it is connected to the top plate, and the top plate moves to the right. This is the final deformation, whereas with the oscillations, you will see that it doesn't just go straight there, it goes through a whole process. Here we can go through the steps of the animation, and we can see the vertical displacements of every single part. Here with step 1, we can see we have a displacement of approximately 7 millimeters downward. Additionally, we see a horizontal displacement of approximately 4 millimeters to the right in step 1. Now, step 2 has a horizontal displacement of 8 centimeters. Now, step 2 has a horizontal displacement of approximately 9 millimeters to the right. The vertical displacement is 1.25 centimeters downwards. Step 3 has a vertical displacement of 1.2 centimeters downwards, which is smaller than the deformation in step 2. This is because the part has passed equilibrium and is now returning to equilibrium. U1 is staying approximately the same. This is due to the part moving down, but not necessarily being forced to the right anymore. In step 4, we can see that the horizontal displacement is smaller at approximately 7.4 millimeters. This is due to part returning to equilibrium. Similarly, with U2, or the vertical displacement, the displacement is a little bit smaller at 1 centimeter. At step 5, we are approaching equilibrium with the vertical displacement being 9.5 millimeters downward. As the part returns to equilibrium, the horizontal displacement is getting smaller as well, and we see that with the resulting horizontal displacement of 6.8 millimeters. Step 6 is really affirming equilibrium position, a horizontal displacement of 6.8 millimeters. Additionally, the vertical displacement is 9.7 millimeters. Finally, confirming that we are at equilibrium, it is approximately 1 centimeter of downward displacement in step 7, with a resulting horizontal displacement of 7 millimeters to the right. To go over the basic animation, we can see step 0, or no deformation, no load applied. Then we can see step 1, step 2, step 3, 4, 5, 6, 7, and beyond where it doesn't move. Going over again, you can see where the part goes down and then back up right in between steps 1 and 2. This is showing that the part has gone past equilibrium in step 1 and then is trying to return to it in step 2 as it slowly moves back up until it reaches equilibrium in step 7 and remains there until the end of the animation. Next, we'll want to verify that our part is really working. Using the vertical reaction forces, we should end up with a resulting downward reaction force we are looking for is at node 1 or ground, which is down here. The resulting reaction force is 700 newtons, which makes sense considering we had a downward body force of 700 newtons. This is proving that we did everything right. Now, I plotted the reaction forces versus time, and I also plotted the horizontal and vertical displacements over time, the resulting reaction force versus time. The reaction force will originally be larger than 700 because the part is deaccelerating on the way down, so the ground force is producing a larger force, but then the reaction force will be below 700 as the part accelerates upwards to equilibrium. This is shown right here where it goes below 700, and then as the part reaches equilibrium and stops moving, we see that it levels out at around 700. For the vertical and horizontal displacements, I selected two nodes, one on the top edge of top plate and the ground reference point. We can see here that the horizontal displacement, or U1, of top plate is non-zero. It is positive as the part initially deforms, and then will start to negate as part starts to reach equilibrium, and here we can see it has reached equilibrium as it levels out. The horizontal displacement of the ground force is 0 because we did constrain it in that direction. For the vertical displacement, we can see that the ground reference point is also 0 because we constrained it in that direction as well. However, the vertical displacement for the top plate is negative, and we can see that it is the opposite of the horizontal displacement, as it is negative when the part is initially deformed, but will become less negative as the part reaches a state of equilibrium. And here we can see the part has reached equilibrium as it is steady and constant.